Welcome back, everybody. Today we're going to take a look at section 4.4, which deals with ways of approximating the percentage of data that lie within certain regions or a certain number of standard deviations from the mean value of your data set. There's two ways we're going to look at things. We're going to thing called Chebyshev's principle. We'll look at first, and then we're going to talk about standard deviations and z-scores, and those are going to be specific to normal distributions, okay? So like it says, the way we go about approximating the percentage of data will be based on whether we have a normal distribution or not. We'll first examine when data does not form a normal distribution. Okay, so Chebyshev's principle. This is used to find the minimum percentage of data that will lie within a certain number of standard deviations from the mean when the data set does not form a normal distribution, okay? Basically, if we're ever asked about, what percentage of data are going to lie this far from the mean, and we're not told a normal distribution, we're going to be using Chebyshev's principle, okay? So we either know nothing about the distribution, we're told it's skewed, something along those lines, okay? Now, the formula looks like this, okay? The minimum percentage of data, P, that will lie within a certain number of standard deviations from the mean is given by P equals 1 minus 1 over K squared. And P is the minimum percentage of data that lie within plus or minus K number of standard deviations from the mean. Okay, so P is the minimum percent, K again represents the number of standard deviations. Okay, so let's take a look at a couple examples and see how this works. So we're told, suppose some data set is skewed. Okay, oh, give this a second, it's lagging, it looks like. Suppose some data set is skewed. Find the minimum percentage of data that lie within 2, 2.5, and 3 standard deviations from the mean. So the fact that we're told the data is skewed and we're dealing with percentage of the data, that tells us we're going to use Chebyshev's principle. All right, so setting up the formula for part A, P equals 1 minus 1 over K squared. We're looking for the minimum percentage of data. We want the value of P. K is the number of standard deviations. So in part A, K is 2. In part B, 2.5. In part C, it's 3. Okay, so all we really have to do for this is about as easy as one of these problems is going to get. So we just drop in the value of K, punch it in, and see what we get back. All right, so P equals 1 over 1 minus 2 squared. You can use a calculator if you need to for this, but it shouldn't be too bad. We end up with 1 minus 1 over 4, which is 3/4, or 0.75, 75% of the data. Okay, so regardless of the distribution of data, if it's skewed or otherwise, 75% of the data at least, it's usually going to be even more than that, but at a minimum, 75% of the data will lie within 2 standard deviations of the mean. Okay, if we want to now see what happens to the percentage of data as we get a little further from the mean, we can now make this 2.5. And let's see what we get. Again, if you need to, you can bring up your calculator and punch this stuff in. It's pretty easy. 1 minus 1 over 2.5 squared. Okay, and look at that, right on the nose we get 0.84. So the minimum percentage of data is 84%. Notice when we punch it in, we get a decimal value back, and again, you should kind of realize, yeah, that's a percentage. That's really 84%. And then last but not least, we can look at what happens at 3 standard deviations, and to do it out quickly, we get 8/9. If we were to punch that in, that would be 0.88 repeating. So about 0.89 or 89%. And what do you notice? The more standard deviations away from the mean we get, the larger the percentage of data we tend to cover, and that should make sense intuitively. Okay, so again, some unknown distribution, or if it's not a normal distribution like this one, it's skewed and you want percentage of data, there's your formula. Now we can kind of go the other direction with this as well as we look at the next example. Okay, suppose 80% of data, says 80% of data will always lie within how many standard deviations of the mean, regardless of the distribution of data. So again, we're talking about percentage of data from the mean. We don't know anything really about the distribution, so we assume Chebyshev here. All right, so my formula, P equals 1 minus 1 over K squared. Now, this time, we're looking for the number of standard deviations from the mean, so we're actually looking for what? Well, we want the value of K. Here we know the percentage of data is 80, so they're giving us the value of P. Now, again, we're not going to let P equal 80. That's not correct. Again, kind of reference what we did up here. P comes out as a decimal. So for 80%, we got to make sure we're using 0.80. Okay? So we can come over here, and now we can solve for K. So we got to do a little bit of algebra here. Different things you can do to begin. I would recommend subtracting 1 from both sides. Be careful, you're going to get a negative 0.20 on the left, and when those cancel, we still have a negative fraction on the right-hand side here, okay? At this point, I'm going to go ahead and multiply both sides by -1. That's just going to make both sides positive, right? So let me clean this up a little. We have 0.2 equals 1 over K squared. I am going to get K out of the denominator by multiplying both sides by K squared. All right, those go. Over here, I'm going to write it as 0.2 K squared equals 1. Divide by 0.2. And then you're going to take the square root of that. Okay, and again, let's just take a look at what that value ends up being here. If I do second square root of 1 over 0.2, we are going to get about 2.24 standard deviations from the mean. So we can go up or down 2.24 standard deviations. Okay, so regardless of the distribution of data, 80% of data is always going to be within just under 2.25 standard deviations from the mean. And what you'll see is that the vast majority of data tends to lie closer to the mean than not. Okay. Next couple examples, slightly more involved. For an unknown distribution, it is known that the mean is 24 and the standard deviation is 3. On what interval will at least 90% of the data lie? Okay, so here's what we know right now. Suppose we have a little number line. All right, the average is 24. We were told that. We're looking for the interval. So basically from here to over here, what are those values that are going to contain 90% of our data? All right, so again, unknown distribution, we're dealing with percentage of data from the mean, we're dealing with Chebyshev's principle. So the formula is right there. And, you know, think about what we have here. We know the percentage is 90, so P is 0.9 in this problem. That's going to allow us to solve for K, the number of standard deviations away, and then we'll do something with that to actually come up with our interval, okay? So let's just worry about K for right now. So let's solve for that. 0.9 equals 1 minus 1 over K squared. And again, very similar algebra here. I'm going to go ahead and subtract the 1 and multiply by -1 on both sides. I'm going to multiply both sides by K squared. And now I'm going to divide by 0.1. So K is going to be plus or minus the square root of this. And what do we get for that? About 3.16, we'll call that. All right, so 90% of the data is going to lie within 3.16 standard deviations of the mean. Okay, so that's going to now help us get the endpoints of our interval. Basically want these numbers, something less than 24 and some number a little bigger than 24. Okay, well, what do we know? We know the actual value of the standard deviation is 3. Okay, we were given that, so I'm going to call that S. And this is the number of standard deviations from the mean we need to travel. We need to go up 3.16 standard deviations above 24. We need to come back 3.16 standard deviations below 24. So basically what we're going to do is we're going to take the number of standard deviations we need, we're going to multiply it by what the standard deviation actually is, and that'll tell us how many units up and back we go. All right, so look, the standard deviation is 3, so I'm going to do, basically I'm going to do this. I'm going to do 24, and I'm going to go back 3.16 standard deviations. Well, the standard deviation was 3. That's going to give me the low end of my interval. For the upper end, I'm going to go 24, and I'm going to go up 3.16 standard deviations. Again, each standard deviation is 3, and so this should give me my interval. So on the low end, we're looking at 14.52, and on the upper end, 33.48. So when we write our answer in an interval notation, we write it in parentheses from low to high. Okay, and now we know if a mean of data is 24 and this is the standard deviation, 90% of the data will have to lie between these two values. Okay, and now last example before we get into normal distributions. A distribution is skewed left, so again we're told right away it's not a normal distribution. If 60% of the data lie on the interval from 72 to 94, determine the mean and standard deviation of the data set. So it's kind of like the last problem in that we're dealing with an interval and a given percentage of data, but now we have the interval and we need to work out the mean and standard deviation. Okay, so let's think about it. Here again is a little number line. We are working on the interval from 72 to 94. And this is going to cover 60% of our data between those numbers. Okay. Well, the mean is actually pretty easy to come up with. Notice in the previous example, the mean is symmetric to the interval. It's right in the middle of the interval. It's always going to be the midpoint. So we don't have to work too hard to get our mean value here. It's just going to be the average of the endpoints of the interval. Okay, and that works out to be 83 here. Okay. And so, you know, if this is correct, we should be going up and back the same amount. It does look like we're going up 11 to go from 83 to 94, and if we were to subtract 11, we would get back to 72. So I'm confident that that is our mean value. Okay, now to get the standard deviation, okay, well, let's again use Chebyshev's principle to get k, the number of standard deviations from the mean, and then we'll figure out what each standard deviation itself is. So here our p-value is 0.6, and so using the formula, we can again use that to solve for k. Subtracting 1, multiply by -1, multiply the k squared over to the left, divide by the 0.4, and take the square root of this thing. Okay, and in doing that, I get approximately 1.58. Okay, and just give that a second. It's dragging a little, probably due to the Wi-Fi. There we go, it just popped up. Okay, so again, here's the rest of the algebra. And this is the number of standard deviations above and below the mean we're going to go. So if you think about like this number line, right, we're basically at x bar, we're going to go up 1.5 of our standard deviations. And if we start at x bar and we go back 1.5 of our standard deviations, that should give us the interval we're working over. Oh, bear with me for just a sec. I might have to reconnect here. Hold on a sec, folks. Okay, back at it. Okay, sorry for the glitch. Happens. So like I said, look, the idea is this. If I start in my mean, I have to go up this many standard deviations. That's what we figured out. And if I start in my mean, I got to go back that many standard deviations. Okay. And basically what we're solving here for is S, the standard deviation. Well, look, we know that if we start at x bar and we add the number of standard deviations, we're going to get to that upper end point of 94. So there's actually an equation we can now use. As long as we know what x bar is, we can solve for s. And similarly, if I start at x bar and I go back 1.58 standard deviations, I know I'm going to be down at 72. So there's another equation that I can use. Make sure I have my s in there. All right, and now all I got to do is sub in for x bar, and I can solve both of these for s. Okay, so for the first one, let me do this. I'm going to sub in for x bar, that's 83. I know I'm going to go up 1.58 standard deviations, and that will take me to 94. So from here, I can subtract the 83. There's 11. This distance of 11 represents this many standard deviations. And then if I divide both sides by 1.58, I get about, let's see, 6.96. Okay, and now I just solve for s. And look, I could use this other equation right here if I wanted to, and it will give me the same end result. If I had used that instead, I subtract, I get negative 158s equals negative 11. When I divide by the negative, I'm going to get that same value back. So it really doesn't matter which of the two equations you use at this point to solve, but there's your standard deviation. So the average was 83, and on average, your grade varied by just a little bit less than 7. Okay? In any event, that's Chebyshev's principle. You're dealing with percentages of data that lie a certain distance from the mean, and we're specifically not dealing with a normal distribution. So it'll say something like skewed or unknown, something along those lines. Okay, now let's move into normal distributions, which is also known as the empirical rule. Okay, some of you have probably seen this before back in high school. This is your bell curve or your normal curve, as it's known. Okay, believe it or not, there's a ton of things out there that form normal distributions in the real world. We will examine some of them as we progress through the course. But for now, we're just really kind of dealing with how do we find percentages of data that lie within certain regions. So in general, if we look at this graph, okay, basically in the middle is our mean value. They're using mu, sometimes I use x bar. But right in the middle of this thing is our mean value. All right, and what this curve is let me give you kind of the formal definition here. It's a continuous probability distribution where values lie symmetric about the mean. Okay, so the mean value is right in the middle of this thing, and we have the same basic thing going on both sides, symmetry about the mean here. Okay. Values are much more common closer to the mean. And less data will lie farther from the mean. Okay, and these regions represent the number of standard deviations. So again, mu is the average, and sigma here is our standard deviation. Okay, so this right here, if I'm using x bar notation, I would write x bar plus s, x bar plus 2s, x bar plus 3s. If I'm just using sample notation versus the population notation that's already on this graph. Okay, that's not a big deal. But basically what this represents is, look, here's a value that's at the mean. Here's a value that's 1 standard deviation above. Here's a value that would be 1 standard deviation below the mean. In general, in a normal distribution, 68% of the overall data is going to lie between 1 standard deviation above or below the mean. That's what this graph is showing us. If we go out to 2 standard deviations, the total percentage of data that will lie within 2 standard deviations of normal distribution is 95%, and a whopping 99.7% of data typically lie within 3 standard deviations. Okay. Now, when we talk about finding the percentage of data, we actually kind of refer to it as the area under this curve. So if you would for a moment, think of this as being a curve above the x-axis whose total area equals 1, representing 100% of the data. Okay. So if we took a chunk like this and we computed the area of that region would be 0.68, and that represents 68% of the data. If I took the area from here to here, that would be 0.95. The area is indicative of the percentage of data that lie in these regions. Okay, and very, very small percentage of the data tend to lie more than 3 standard deviations away from the mean when we have a normal distribution. Okay, so this is kind of the nuts and bolts of this thing. You don't have to memorize these numbers at all, these percentages. Our calculators actually can come up with the numbers we're going to need very, very easily, and I'll show you that in a moment. Okay. Now, just to kind of investigate a little more what this stuff is all about, let's suppose we have a normally distributed data set. Notice how we're told that. The mean is 80 and the standard deviation is 6. Let's go ahead by hand and kind of just sketch one of these curves and discuss a few things here. All right, so I'm just going to kind of draw this curve out. Oops. Okay, so coming in here. All right, so the mean is 80, so I'm going to draw a line vertically down the center, and I'm going to call that 80. Okay, that's our average. Now we know that the standard deviation is 6. So I'm going to go, here's another line. This represents being 1 standard deviation above the mean. Well, what's 80 plus 6? 86. So that represents the value that's 1 standard deviation above. If I add another 6, I'm now 2 standard deviations above, and we typically go up to 3. And if I subtract 6, I'm down to 74. That would be 1 standard deviation below the mean. 68 is 2 below. And 62 would be 3 below. Okay. So, basically in this set, we would say, you know, about 68%, if this represents like test grades, about 68% of the students scored between a 74 and an 86. About 95% of the students scored between a 68 and a 92. And just about every student scored between a 62 and a 98 here, based on the data. Okay? But this is labeling, you know, the curve. And now, what I want to kind of relate this to is the next topic, which are z-scores. Okay? A z-score represents the number of standard deviations away from the mean value a particular data value lies. Right? It tells us the number of standard deviations above or below the mean the data value itself lies. A positive z-score indicates the data point was above the mean. Negative means it was below. So using the example above, that 62 would have a z-score of -3 because it is 3 standard deviations below the mean. That's what a z-score represents. Okay, the number of standard deviations a particular data point lies above or below the mean. 68, we can see above, is 2 standard deviations below the mean. That would have a z-score of -2. 74, as you could probably imagine, has a z-score of -1. How about 80 itself? Is 80 above the mean, below the mean? It is the mean. It's not above or below the mean. It's 0 standard deviations away from the mean. So that would have a z-score of 0. That means that the value was the mean itself. 80 is the mean. 86 is 1 above the mean, 1 standard deviation above the mean. That would have a z-score of +1. 92 has a z-score of +2. 98 a z-score of +3. Okay, so the z-score refers to the number of standard deviations above or below our mean. Now, those are nice, convenient numbers to work with, but you're not always going to have that. So, like for example, what about 83? 83, if you think about it, would be right here, kind of in between 80 and 86. Well, if this is 1 standard deviation above the mean, this is actually a half a standard deviation above the mean. So you can have decimal values and fractions for your z-scores. 83 would have a z-score of 0.5. It's half a standard deviation above the mean here. And then we can ask other numbers like 90 and 55, and that can be a little trickier, especially if like a number like 90 is kind of like right here. It's not really the midpoint of that interval, you know. So there's a better way. We can tell 90 is going to have some positive z-score, and as we look at this, it looks like 90 would be somewhere between 1 and 2 standard deviations above the mean. So it's going to be like 1 point something. We can figure that out. In the next example, we're talking about a score of a 55. That's like way down here. We would expect that to have some sort of a negative standard deviation, probably much lower than -3. So how do we actually go about computing these values? Well, here's the formula for it. To compute a z-score, basically what I'm doing with the numbers up here in relation to my mean and standard deviation to get my z-score is the following. Okay, we take the actual data value, which we sometimes call x sub I, we subtract the average value and we divide it by the standard deviation. Okay, that's the formula for your z-score, where x sub I is the actual data value, x sub 1, x sub 2, x sub 3, sub 4, whatever. X bar is the average mean value, and S again is our standard deviation. So I want the z-score for 90. I'd say, look, z equals the actual value was 90 minus the average of 80 divided by my standard deviation of 6. Okay, and then I can punch 10 over 6 into the calculator here, and we get our z-score. So let's see. And that has a z-score of about 1.67, which is kind of what we said. We expected it to be between 1 and 2 standard deviations above the mean, a little closer to 2 than to 1. Okay, and then notice also that it's positive, an indication that it was above the mean. And then if I want the z-score for 55, take the actual value minus the mean over the standard deviation, and let's see what we get here. So 55 minus 80 is -25 over 6 is -4.17 if we round it 2 places. So a 55 is more than 4 standard deviations below the mean. Okay? In any event, this is how we calculate the z-score. And that now leads us to the last part of this, which is the p-value. The p-value actually represents the percentage of data that lie in a certain region under the normal distribution, and it's very related to the z-score. Okay, so like the p-value for the data above, for this example, to be within 1 standard deviation of the mean. So basically, like if I want the p-value for being within 1 standard deviation of the mean, I could go up or down 1 standard deviation. The p-value represents this percentage of data, and as we saw up above, within one standard deviation of the mean, we're looking at 68% of the data. But that's what's meant by the p-value, okay? And we can get these right on the calculator, so about 0.68. So how do we do it on the calculator? Well, that's what I'm about to show you. Okay, so to do these on the TI 83 and 84s, okay, we're actually going to go second vars, and it's going to be number 2, normal CDF. Don't use the first one, that says PDF. We're using a continuous distribution, so a normal CDF is what we want, okay? And now, the formatting on your calculators might be a little different. Mine looks like this. The first thing I need to input is the mean value, okay? So I'm going to use this example we were going with. All right, so in this example, the mean was 80. So I'm going to say 80. Then we got to hit the comma button and we tell it the standard deviation. The standard deviation for this problem was 6. Then I hit a comma and I tell it, look, I want the percentage of data between these two numbers. So I give it the lower number, give me the average is 80, the standard deviation is 6. Tell me the percentage of data between 74 and 86. Close it up. Whoops, make sure you get that right. And hit enter. Okay, and that is not what I was going for at all. Let's try this again. Oops. Wish that would stop doing that. folks. I don't know why this is not working. It should be. Give me just a sec. Apologies. All right. Hidden things in slightly wrong order, it looked like. So let me back up here. So again, it is second vars, okay? It's normal CDF, but the way I am, you're actually putting the lower value in first, okay? It's going to be lower value, the upper value, the mean, and then the standard deviation. So again, we wanted the percentage of data between 74 and 86. So if yours just says lower, you're going to go 74. If your screen looks like mine, you're going to do like I did, 74. Now the upper value was 86, the average was 80, and the spread was 6. Okay, and again, if you have a screen that actually asks you for these values, it's a little easier to punch in, I think. And there you go, and there's our about 68% probability that we actually saw when we did it by looking at the graph. Okay, but you're not going to have to look at graphs to do this stuff. You're gonna be using your calculator, and ideally, no more hiccups on that end of things. All right, so again, I'm just kind of a weak internet connection today. It seems I'm cutting out a little bit, so bear with me coming back in here with the examples. But rest assured, we're almost done with this lesson. Okay, and hopefully you're getting this. Okay, so again, there was that 68%, and then we got it on the calculator. So again, normal CDF, low value, high value, average, mean. Now, one thing to know about this diagram is that in theory, this distribution curve positive infinity and back to negative infinity in theory, and that's going to play a role when we come to doing some problems, like we're going to see in a moment, okay? So let's take a look at this last example now and see how we can use the calculator to get these different percentages and talk about this thing called a percentile value. So math SAT scores tend to form a normal distribution with a mean of 500 and a standard deviation of 80. Suppose that 200,000 students took this particular math SAT exam, okay? What is the Z-score for a student who scored a 600, okay? So the calculator doesn't really give you the Z-score. That you got to use the formula for. The calculator gives you the p-values, though. Okay? So if we just want the Z-score, what we're going to do is we're going to use our formula. Z equals the actual value, 600, minus the average. Just jot those down. Over the standard deviation. So whatever 100 over 80 ends up being, that is 1.25. Okay, so a student who scored a 600 on the math section was 1 1/4 standard deviations above the average grade, okay? A person who scored 600 did better than what percentage of other test takers? So here's where we're basically looking for the percentage, a percentage, okay? So we're going to end up using the calculator. Now here's how I like to do these. I like to draw kind of like a little normal distribution curve to represent what's going on. It's averaged at 500. I'm looking for the percentage of data that came back 600 or better in this case. Excuse me, I'm shading the wrong way. Whoop. A person who scored let me read this. A person who scored 600 did better than what percentage? Yeah, so we did better than the rest of this group to the left. So indeed, we want to shade to the left here. And basically now I want to know, well, what percentage of data would that cover? And that's where I can use the calculator. All right, but we got to be careful of what we're calling lower, upper. We know what the mean is, and we know what the standard deviation is, okay? Basically, look, the mean is 500, the standard deviation is 80. Those values we know. When we talk about lower and upper, we're basically saying where are we shading from and where are we shading to. The upper is a little more obvious here. We're shading up to 600, so that's our upper value. In terms of lower, you know, intuitively you might want to use 0 because realistically, like a 0 is the worst score you could get. But if you remember what I said a moment ago, in theory, these things go back to negative infinity and up to positive infinity. These number lines go left and right forever. And so basically, you know, we want to go back to negative infinity. Well, how do we say that on the calculator? We basically give it a very, very large negative number of the form -10 to the 99th power. So anytime we're shading all the way to the left, we're going to use negative 10 to the 99th power. So watch as I punch this in. I'm going to go, let me clear this, second bar, okay, lower, negative, this is the negative key, not the minus key, you'll get an error message, negative 10 to the 99th power. This off at 600, I want the percentage between negative infinity and 600, if the average is 500, and the standard deviation is 80. Okay, and we should get the percentage data, so that's about, a little more than 89% of the data. That's the p-value, as we call it. So the p-value about 0.8944 if I go 4 decimal places. Cut off a little bit. Okay, that's the p-value. So someone who scored a 600 did better than almost 90% of the test takers. Okay? And that leads us to part C, the percentile rank. The percentile rank is this number. It's value that it's the percentage of the population you did than or equal to. Okay, so if I wanted to know the percentile rank of a 600, well, they did better than that percentage of test takers. That would be at the 89th percentile. Okay, someone who scored a 500 exactly mean would be at the 50th percentile. Someone who scored a 500 did better than half the students, did worse than half the students. They're at the 50th percentile. More practice on the calculator. What percent of test takers scored below a 450? So again, if you do a little diagram, it can be a little bit helpful here. Average was 500. I want the percentage that scored below a 450. So for lower, again, I'm going negative infinity. Upper is 450. Our mean 500, and our standard deviation is still 80. So I'll just go right back in here. And let's see, lower, negative 10 to the 99th. Up 450 this time. Same average, same spread. Okay, and we're looking at about 26.6%. So the p-value here is about 0.26. That would round up to 60, 2660. Okay, so they didn't do quite as well, a little better, about the 26th, 27th percentile. Okay, let's see what percentage of students scored above a 700. The high end of things here. So again, we're centered at 500, and I want the percentage that scored 700 or above, so I'm going to shade to the right this time. So now the lower value, we're low at 700, and we're shading up to the right. We're going out to positive infinity. We're going to call that positive 10 to the 99th for the calculator. Once again, the average and the standard deviation are the same. And so let's see what we get. And 700, 10 to the 99th. Oops. Average spread. Very small percentage, 0.0062. If you move the decimal places 2 over, you're looking at 0.62%. Okay, less than 1% of the population scored above a 700. Okay, if we want to go between two values, lower and upper, just those values themselves. What percent scored between a 400 and a 600? So lower, I'm not going to write it all out now, just punch it in. Lower is going to be 400, upper 600, and average and spread. Okay, so a little under 79%. So here our p-value is about 0.7887. Okay, again, a little under 79% of students would have scored between 400 and 600, within 100 points of the mean. And now part G, approximately how many students scored in this range, okay? So look, to figure this out, we know the percentage of students. We just did that in part F. That percentage of the total scored between these values, want to know the actual number of students, then we're just going to apply this percentage to the entire population, which was 200,000. So that's why that value was given before. Okay, so here we're just going to take that percentage of the population. And what do we get here? Looking at about 157,740 students total that scored in that range. Okay? Now, in terms of parts H, I, and J, when we're actually, here we're actually looking for the score that's better than 90% of other scores, 95 and 99. So basically, here, kind of the same idea, but now for like part H, I want this value. I don't know what it is, but I want that to cover 90% of the data. Okay, well again, there's a way to do that on the calculator. We're going to go back into second bars, but this time we're going to go to inverse norm. Inverses are like kind of going backwards, doing the opposites. We're doing the inverse norm. And again, give me a moment to play around here. I want to say it's average, comma, spread, comma, the percentile value. If we want to be at the 90th percentile, we're going to write that as 0.90. And then what the calculator should do is say, well, look, if this is your average and this is your spread, here's the value that'll show up at the 90th percentile. Except I now have it backwards. So give me a second. I might be like flipping things around. For just a moment. And there it is. Okay, and that makes sense. 602 being right up here is going to be certainly above the mean. And actually, if we look over here, a 600 was a little more than the 89th percentile, so a 602 makes sense. Okay, so the input is this. It's actually, it might ask you for the area. That's the percentile value. You got to make sure it's a decimal. Average, then your standard deviation. Okay, so a score of 602.5. Okay, you can say 602 or 603, I'm fine with that, is going to be better than 90% of the rest. Well, let's see what's better than 95% of the rest. So again, come right back into this, number 3, and now just change that to 0.95. Same average, same spread. Okay, a score of about 631 or 632. And for the 99th percentile, just go back in and make that 0.99. And a 636 did better than 99% of the rest of the population. Okay, folks. So again, this whole section deals with approximating percentage of data, finding standard deviations for Chebyshev's principle periodically. But really, the big thing is, look, you got kind of a normal distribution. We use the calculator to get that stuff. If it's any other sort of distribution, we're using Chebyshev's principle. Okay, folks, as always, if you have any questions or anything, reach out, and hopefully all is well.